4.3, connecting f prime and f double prime with the graph of f, part 3. I can apply the second derivative test for local extrema, and I can use derivatives to describe the graph of a function. Those are your objectives for this lesson. The second derivative test for local extrema. Part 1, if f prime of c equals 0, so the slope of your original function is 0 at whatever point, and f double prime of c is less than 0, so the slope of your derivative is negative, then f has a local max at x equals c. If f prime of c equals 0, so again the slope of your original function is 0 at point c, and f double prime of c is greater than 0, so your first derivative has a positive slope, then f has a local minimum at x equals c. Okay, this test requires us to know f prime only at c itself and not in an interval about c. So that's kind of nice. We only have to know the f prime at a point instead of on the interval. However, this test fails if f double prime of c equals 0 or if f double prime of c fails to exist. When this happens, we need to go back to the first derivative test for local extreme values. Example 6. Find the extreme values of f of x equals x cubed minus 12x minus 5. We're going to use the second derivative test, so the first thing that we need to do is find the second derivative. Okay, so f prime of x is 3x squared minus 12. F double prime of x is 6x. Okay, the points that we're going to evaluate with this are our critical points. So it's what we find when we set the first derivative equal to 0, as you can see here. So first derivative equals 0, and then second derivative we're looking for its sign plus or minus. So let's take our first derivative and set it equal to 0. 3x squared is 12, so x squared is 4, so x is plus or minus 2. Okay, so I'm going to do f double prime of 2 is 6 times 2, which is 12, and f double prime of negative 2 is 6 times negative 2, which is negative 12. And looking back at our derivative test here, when the second derivative is negative, less than 0, I have a local max at that point. So right here, negative, this means I have a local max at x equals negative 2. Since this is positive, I have a local min at x equals 2. And I'm going to stop right there with this problem. So that's all I really was looking for. Example 7, this is a 4-part one, you can see it. Let f prime of x equal 4x cubed minus 12x squared. Identify where the extrema of f occur. Well, I know that the extrema are going to occur where f prime is equal to 0. So why don't I go ahead and set this equal to 0. Okay. I'm going to solve by factoring. So these both have 4x squared in common, leaving an x minus 3. So either 4x squared equals 0 or x minus 3 equals 0. Get x equals 0 or x equals 3. So these are where my extrema are going to occur. I don't have any points where this isn't going to exist, or I have endpoints, so those are the only places where I have extrema. Part B. Find the intervals on which f is increasing and decreasing. To do this, I'm going to need to use my sign chart. So let me set that up quickly. Okay. So I'm going to have my sign of f prime and behavior. Okay. My first interval will be from negative infinity to 0. Second one will be 0 to 3, and the last one greater than 3. Okay. If I plugged in a -1 for my x, so x equals -1, my derivative is 4x squared times x minus 3, so I would have -1 squared is positive, so 4x squared is positive. -1 minus 3 is a negative, so this would be negative. If I plugged in a +1, still going to have a positive factor here on the outside using this guy. And then I would have a negative on the inside. And then that's a negative. If I plugged in a 4, I would have positive on the outside and positive on the inside. 4 minus 3 is 1, so this is positive. So this means here I'm decreasing, increasing. Okay. So I could write this out instead of just leaving the chart to say that f is decreasing on negative infinity, 0, and 0, 3. And f is increasing on 3, infinity. Okay. Part C, find where the graph of f is concave up and concave down. Well, for this, I need my second derivative. So 4x cubed minus 12x squared is f prime. So f double prime is 12x squared minus 12x, or 12x x minus 1. Okay. And I know I'm going to use my sign chart. But first I need to find my critical points. What am I doing? So I need to set this equal to 0. So 12x equals 0 means that x is 0. X minus 1 equals 0 would mean that x equals 1. So my critical points are at 0 and 1. So I'm going to have an interval from negative infinity to 0, 0 to 1, and 1 to infinity. Okay, and I want to know the sign of f double prime and the behavior. So is it concave up or concave down is what I want to know. Okay, so let's plug in a negative number for x in here. So I have 12x x minus 1. If I plug in a negative 1 here, I'm going to have a negative outside and a negative inside. And negative times negative is positive. If I plug in x is 1/2, I'll have a positive outside, but a negative inside, so negative. And last, if I plug in, I don't know, a 2, so for my last interval, I have positive on the outside and positive on the inside, so that's a plus. So this is concave up, concave down, concave up. Okay. So I'm going to write that my graph is concave up on the intervals -infinity, 0, and 1, infinity. It is concave down on the interval 0, 2. Okay, this is my answer for part C. Part D, this is the last part of this example, which is the last part of this lesson. Let's push through it, power through it. Okay, so first, what I want to do is summarize my two tables. So I'm going to combine my intervals kind of onto one table. Get them all up here. So I have x is less than 0, x is between 0 and 2, and x is between 0 and 3, x is greater than 3. Okay, on this interval, my function is decreasing and concave up. Second interval, I'm decreasing and concave down. Third interval, decreasing, concave up. Last interval, increasing and concave up. So this is a lot of information here. We are going to try to make a graph. I'm going to try to do the best that I can with the airliner here. Hopefully I do a decent job. So my graph is going to look like this. Decreasing means it's going down. Concave up is like a little cup. So that's my first part. It's concave up. You could put some water in that. And that would be x equals 0 right here. So x equals 0. Now I'm going to decrease some more, but I'm going to be concave down. So like that. Okay. So this would be x equals 2. Okay. I'm going to keep decreasing, but I'm going to be concave up again. So like that. Okay. And this is x equals 3. Now the rest of my graph is increasing and concave up. So it should be like that. That's not too bad. Okay. So this would be a possible graph for f of x. Your graph might look a little different. This is what my graph looks like. And that is it for 4.3.